So let's have a look at this formula and see how we can turn that scale into something readable. So let's say we take a solution. Let's say we have a solution, and the solution has a concentration, and we'll pick something off that line. We'll say it has a concentration of 10 to the minus 4, okay, moles of hydrogen ions. Okay, so that's the concentration of the hydrogen ions, 10 to the minus 4. The question will be very simple. What's the pH? So we just take our pH formula. So pH is equal to minus log to the base 10 of the hydrogen ion concentration. And our hydrogen ion concentration is 10 to the minus 4. And again, this can be tapped straight into the calculator without too much hassle, and you end up with pH is equal to 4. That answer equals 4. So basically, it's a way of turning each one of those indices, 10 to the minus 9, 10 to the minus 7, all those into just a number. That's all it does. Something you may be wondering at this stage is, what actually does pH stand for? Well, pH stands for the power of the hydrogen ions. That's what pH stands for. And what it means by that is the stronger the hydrogen ion concentration, the more acidic it is. So there's your first question, and then a lot of questions are based on this. Let's go take another example. So we say that's example 1. Let's have a look at example 2. So in this one, let's say we want to calculate the pH. So calculate the pH, and let's say the hydrogen ion concentration. So this hydrogen ion concentration is 7.1 multiplied by 10 to the minus 7. And it will give units then, which is moles per litre. So again, look at what the question's asking you to do. It's asking you to calculate pH. So if you're asked to calculate pH, it's minus log to the base 10 of the hydrogen ion concentration. So it's a simple substitution. Minus log to the base 10 of 7.1 multiplied by 10 to the minus 7. All straight into the calculator, and you get out a number of 6.15. So you've got a pH of 6.15. Remember, pHs aren't just whole numbers. They can exist in between as well. Let's take something maybe a little bit harder. So example 3. So in this one, what we'll do is we'll be asked to calculate the hydrogen ion concentration. If the pH is 3.7. So your clue in this one is this particular part here. The pH is 3.7. So if we take pH is equal to minus log to the base 10 of the hydrogen ion concentration, because you're told the pH is 3.7, you're actually being given the answer at the start. 3.7 equals minus log to the base 10 of the hydrogen ion concentration. Now, what's the question asking for? It's asking for the hydrogen ion concentration. So we need to get this on its own. So we have to sort out this minus logarithm. Now, if you've done honours maths, you should be able to do this without too much hassle. If you've done ordinary level maths, you've never seen this before because logarithms are not on the course. So pay attention to this, and we'll try and show you a quick way of doing this. So the first thing I would do is I need H plus on its own positive value. So the first thing I'm going to have to do is get rid of the minus in front of the log. So that's easy. You just bring it over the other side of the equals. So we end up with minus 3.7 is equal to log to the base 10 of the hydrogen ion concentration. My next step here is not mathematical. I just maneuver the equation around a small bit so it's a little bit easier to work with. And I always write it as log to the base 10 of the hydrogen ion concentration is equal to minus 3.7. I haven't done any maths to that. I've just turned it around. Now, when I'm doing logs, once I have them in this format, this is the way I do it. I do it via a loop method. And what I do is I start with the 10, and I draw a line all the way around like this back to the hydrogen ion concentration. And what I do is I take my number, the first number that I come across, which is 10. Then I take my next number that I come across, which is minus 3.7, and I put that as a power. And that equals the last number, or the last thing that I come across, which is here, which is your H+. Now, and I've been teaching honours maths over the years, that's always the way I've taught logarithms. You may have your own different way of doing it. Of course, there's, you know, you can do log B A equals C. You can do the log back system if that's what your teacher has taught you and that's what you know, and there's nothing wrong with that. I generally always start over here with the 10, I run around to the minus 3.7 and I get my hydrogen ion concentration. So 10 to the power of minus 3.7. So when you tap that into the calculator, you might get something like this. So you get 0.000199952 and a couple of other bits is equal to the hydrogen ion concentration. Now you can leave it at that, or your calculator may give you something in scientific notation. So in scientific notation, which is probably what you should be doing, you need to leave it at 1 point, in this example, 9952. The reason why is in scientific notation, your scientific notation has always got to be between 1 and 10. So we're dealing with the number 1.99, and that's going to be 10 to the power of, so we've got to move the decimal point 1, 2, 3, 4 places, so it's 10 to the minus 4, and that's our hydrogen ion concentration, and that's what the question is asking us. So again, a little bit more difficult when you're given the answer, and a lot more difficult if you're just doing ordinary level maths or you don't fancy doing logs. Go back through this example a couple of times just to make sure that you understand it and where everything comes from. Let's move on with a couple more examples and a little bit more theory. So now what we're going to do is move on to the pH of strong acids and strong bases. So these are the next calculations. Now in order to do these questions, you need to be able to, at a glance, be able to figure out what is a strong acid and what is a strong base. Now what I've done is written down the 3 most common strong acids that you'll be dealing with, and for the most part you'll only be dealing with the first 2. We've hydrochloric acid and sulfuric acid, HCl and H2SO4, nitric acid then at the end, and then strong bases would be hydroxyl molecules with maybe sodium or potassium in them. So there's examples of strong acids and strong bases. Now what we'll do is we'll have a look at a quick calculation. So let's look at this first question. So the first question says calculate the pH of a 0.01 molar HCl solution. So straight away we're trying to break up this question, and normally what we would do here is we would say fine, let's get the pH of something. So you would normally write down pH then is equal to minus log to the base 10 of the hydrogen ion concentration, and you go fill in your hydrogen ion concentration. The problem we have here is there is no hydrogen ion concentration. We don't know what it is. It doesn't give it to us in the question. So we're going to have to try and figure that out in order to work out the pH. How do we work out the hydrogen ion concentration? Well, bear in mind what an acid does. An acid is a proton donor. An acid is a substance which dissociates, especially a strong acid, will dissociate fully in solution. Now what does dissociate mean? Dissociate means that your acid will break down into H plus ions and Cl minus ions. Now what have we got here? We've got 0.01 molar HCl solution. So according to our equation, we have one of these and we've one of these in terms of the coefficient. So the coefficient is 1 here and the coefficient is 1 here. It's obviously just not written in, it's not explicit. So it reacts in the ratio 1:1. Because of that, if we have a 0.01 molar solution of HCl, we should have 0.01 molar of the H plus ions. And this is where we get our hydrogen ion concentration from. So now all we've got to do is pop it into our pH equation. So now we have pH is equal to minus log to the base 10 of our hydrogen ion concentration, which comes from there, and we just put in 0.01. You pop that into your calculator and you get your pH. That works out at 2. Now remember, your answer should make sense. You're finding the pH of a hydrochloric acid solution, which means it should have a low pH. This makes sense. If you got a pH there of 13 or 12, you know you've done something wrong with your calculation. Let's try it again with the next question. This next one is calculate the pH of a 0.4 molar H2SO4 solution. You're going to do exactly the same thing here. You're going to write down your pH is equal to minus log to the base 10 of the hydrogen ion concentration. But we don't have a hydrogen ion concentration. We just have molarity. So for strong acids and strong bases, they always break down, H2SO4. So what does this form, H2SO4? Well, it will donate hydrogen ions, but how many of them? Well, it'll donate 2 of them. So we've got 2 H pluses plus SO4 dinegative. The sulfate ion is always dinegative. So that's why we have 2 H pluses to balance the charges out. Now, if we have H2SO4 and the question says that we have 0.4 molar solution, because we have a ratio of 1 is to 2 on this side, 0.4 molar of the H2SO4 will produce 0.8 moles of the other one. So now what we've got to do is start filling in our number. pH is equal to minus log to the base 10 of our hydrogen ion concentration. And you pop in your 0.8. Now some students might correctly say, well, hang on, you're trying to find the hydrogen ion concentration, not 2 hydrogen ion concentrations. But this here is the concentration of your hydrogen ions. Regardless of whether it's 2 or not, it is the concentration. So again, pop that into your calculator and you get a pH value then. So that works out at 0.097 and a few other numbers, but we leave it at 0.97. So again, this makes sense. This is a very, very strong acid. In fact, it's stronger than the previous one, which also makes sense because H2SO4, sulfuric acid, is a stronger acid than hydrochloric acid. And one of the main reasons why is because it donates 2 protons each time compared to hydrochloric acid, which only donates 1 proton each time. On to this next question. Calculate the pH of a solution containing 5 grams of sulfuric acid in 250 cm cubed of solution. I'm going to do this in the next part as I'm running out of time in this video. We'll come back to that.